and welcome to tonight's Space Sleep Story. If you appreciate what we do here, please like or subscribe for future relaxing nighttime space journeys. Tonight, we embark on a journey not through space, but through time, tracing Mars's 4.6 billion year biography, from molten newborn world to the frozen desert we observe today. So settle into your most comfortable position, close your eyes, and prepare for a deep time meditation spanning the entire history of our neighboring planet. Before we begin, let us prepare your body and mind with gentle breathing. Take a slow, deep breath with me now. Inhale gently for 4 counts. Hold the peace. Exhale for 6. Feel your body releasing into stillness. Your breath connects you to this moment, while we prepare to contemplate timescales beyond human comprehension. Breathe naturally and let my voice guide you through deep time. Another gentle breath as we continue our preparation. This time, notice how your chest rises and falls, oxygen entering your body, carbon dioxide leaving. This exchange of gases has occurred on Earth for billions of years. Let my voice be your guide. Hold this peaceful moment. Feel the stress of the day leaving your body. With each breath, you release a little more into relaxation, preparing to witness planetary birth and transformation. $4.6 billion years ago, before Earth had multicellular life, before dinosaurs, before even the first cells, Mars coalesced from the protoplanetary disk surrounding our young sun. Countless planetesimals collided, merged, grew through gravitational attraction. Within just 10 million years, a geological eye blink, a planet-sized body existed. Heat from these violent impacts and radioactive decay within melted the interior. Dense iron and nickel sank toward the center, forming a core. Lighter silicate rocks rose, forming mantle and eventually crust. By 4.5 billion years ago, Mars had differentiated into the layered structure characteristic of terrestrial planets. This early Mars was nothing like the frozen world we see today. The planet glowed red hot from accretion energy, its surface molten, constantly reshaped by impacts still raining down from the young solar system. Volcanic outgassing released water vapor, carbon dioxide, nitrogen, and sulfur dioxide from the interior. These volatiles accumulated, forming Mars's first atmosphere. Scientists estimate this early atmosphere may have been several bars in pressure, compared to the modern atmosphere of just 0.006 bars. Mars was born violent and hot, but atmospheric protection was building, stage set for transformation. At the heart of young Mars, something remarkable began. The small iron core, approximately 1,830 kilometers in radius, remained molten from formation heat and radioactive decay. Convection currents formed in this liquid metal, creating what scientists call a planetary dynamo. This dynamo generated a magnetic field extending into space around Mars. The field was weaker than Earth's, perhaps just 0.1 to 1% of modern Earth's magnetic strength, but it existed. For approximately 500 million years, from 4.1 to 3.6 billion years ago, Mars possessed a protective magnetosphere, deflecting the solar wind just as Earth's field does today. Mario Acuna, principal investigator for the magnetometer aboard Mars Global Surveyor, described the moment of discovery in 1997. When we first measured Mars's magnetic field from orbit, we expected a weak induced field from solar-wind interaction. Instead, we found strong crustal anomalies in the southern highlands, up to 1,500 nanoteslas locally, 30 times stronger than predicted. These are fossil magnetism. Rocks magnetized billions of years ago, when Mars had a global dynamo like Earth's. That field shut down around 4 billion years ago. We were seeing the ghost of a dead magnetic field, frozen in ancient crust. Between 4.1 and 3.8 billion years ago, the inner solar system experienced intense bombardment. Asteroids and comets left over from planetary formation crashed into the young planets. Mars received thousands of large impacts during this period. The largest created Hellas Basin, 2,300 kilometers in diameter, formed approximately 4 billion years ago. Argaea Basin, 1,800 kilometers across. Isidis Basin, 1,500 kilometers wide. Each major impact released enormous energy, equivalent to 10 to the 27th joules for the Hellas impact, blasting atmosphere into space, potentially sterilizing the surface with heat, yet also delivering water and organic molecules from comets. This bombardment era created the striking dichotomy still visible on Mars today. The southern highlands stand 4 to 8 kilometers higher than the northern lowlands, heavily cratered, preserving a surface over 4 billion years old. The northern lowlands show far fewer ancient craters, suggesting they were resurfaced later in Mars's history, erasing the bombardment record. How this hemispheric asymmetry formed remains debated. Perhaps a single giant impact on the northern hemisphere created it, or internal convection processes drove the difference. Either way, two distinct geological provinces were established, setting the stage for Mars's divergent evolution. As the heavy bombardment declined around 3.8 billion years ago, Mars entered what scientists now recognize as its golden age. The thick carbon dioxide atmosphere, possibly half a bar to 2 bars in pressure, created greenhouse warming. Water vapor added to the greenhouse effect. Surface temperatures rose above water's freezing point, possibly reaching 0 to 20 degrees Celsius on average, compared to the modern negative 63 degrees. For the first time, and perhaps the only time in its history, liquid water became stable at Mars's surface. Lakes formed in crater basins. Rivers carved branching valleys into the ancient highlands. Rain may have fallen from clouds. Mars was habitable. Valley networks carved during this era resemble terrestrial river systems. Branching patterns suggest sustained water flow over millions of years, either from rainfall or groundwater seeping from the subsurface. These valleys are concentrated in terrain dating to 3.8 to 3.5 billion years ago. Gale Crater, where the Curiosity rover now explores, contained a long-lived lake with sediment layers tens to hundreds of meters thick. Jezero Crater, Perseverance's landing site, had a river delta depositing sediments 3.8 billion years ago. The northern lowlands may have held an ocean or series of seas, though shoreline features remain debated among scientists. Mars held enough water to cover the entire planet 100 to 1500 meters deep. Phyllosilicates, clay minerals requiring neutral pH water in long-term contact with basaltic rock, formed widespread across ancient Mars. Orbital spectrometers have mapped these clays in terrains 3.8 to 4.1 billion years old. Their presence indicates not just fleeting wetness, but sustained, benign conditions. Water chemically weathering rock over geological timescales. Environments potentially suitable for prebiotic chemistry, or even the origin of life itself. Bethany Ellman of JPL and Caltech studies these mineral maps. Clay minerals are concentrated in ancient terrains. Later epochs show sulfates, suggesting acidic water. The clay to sulfate transition records Mars's climate transformation from benign wet world to acidic, drying planet. For perhaps 300 to 500 million years, from approximately 3.8 to 3.3 billion years ago, Mars offered habitable conditions. Liquid water, chemical energy sources, protective atmosphere, moderate temperatures. On Earth, life emerged within approximately 700 million years of planetary formation. Mars had comparable, or even longer, habitability windows. Whether Martian life actually originated during this era remains one of science's greatest open questions. But the environment was suitable. The stage was set. If life arose anywhere beyond Earth in our solar system, ancient Mars is a prime candidate. John Grotzinger served as Curiosity's project scientist from 2012 to 2019. He described analyzing mudstone at Yellowknife Bay in Gale Crater. When Curiosity drilled into that mudstone and analyzed its chemistry, I got chills. This wasn't rock that briefly got wet and dried. This was lake-bottom sediment. Long-lived lake with fresh water, neutral pH, low salinity, chemical energy sources from sulfate and sulfide minerals. Conditions you'd expect microbes to thrive in. This lake existed 3.5 billion years ago and lasted millions of years. Mars had a habitable environment. Whether life actually emerged, that's still an open question, but the environment was suitable. Steve Squires, principal investigator for the Spirit and Opportunity rovers, spent 15 years following Opportunity's journey across Meridiani Planum. We designed the rovers to search for evidence of past water. The question wasn't, was Mars ever wet? But how wet? How long? How recently? Opportunity landed on Meridiani Planum and immediately saw hematite blueberries scattered everywhere. Concretions formed in water. The rover spent 15 years exploring rocks deposited in an ancient lake or evaporating sea 3.8 billion years ago. Mars wasn't just damp, it was soaking wet, potentially habitable for millions of years. Imagine those ancient shores, water lapping against red rocks under a thicker sky. But even during this golden age, Mars's fate was being sealed. Around 4 billion years ago, catastrophe occurred in the planet's core. The small iron core cooled below the critical threshold required to maintain convecting motion. The dynamo shut down. The global magnetic field collapsed. Without magnetic protection, the solar wind began directly impacting Mars's upper atmosphere. Energetic particles from the Sun collided with atmospheric molecules, ionizing them, accelerating them to escape velocity. Over hundreds of millions of years, Mars began losing its atmosphere to space. The protective blanket that maintained surface warmth slowly stripped away. Jack Connerny, a NASA planetary magnetosphere expert, explains the connection between magnetic death and habitability loss. The magnetic field discovery fundamentally changed our understanding of Mars's evolution. Early Mars had a protective magnetosphere deflecting solar wind like Earth does. When the core cooled and the dynamo died, protection vanished. Solar wind began directly stripping atmosphere. Over hundreds of millions of years, Mars lost 99% of its air to space. The timing matches exactly. Magnetic field died 4 billion years ago. Atmospheric loss accelerated immediately after. Warm, wet climate ended. Magnetic death sentence for habitability. In the southern highlands, remnant crustal magnetism preserves memory of this lost field. Rocks magnetized billions ago when the dynamo still operated. The northern lowlands lack these strong magnetic signatures, suggesting they were resurfaced after the field collapsed. Volcanic flows or impacts erasing the magnetic record. Mars Global Surveyor's magnetometer mapped these anomalies from orbit, creating a fossil record of planetary magnetic history. Strong fields in the ancient south, weak fields in the younger north. A planet remembering what it once possessed and lost. The evidence for atmospheric escape exists in the air itself. Modern Mars's atmosphere shows extreme enrichment in heavy isotopes. Deuterium, heavy hydrogen, appears 5 times more abundant relative to normal hydrogen than in Earth's atmosphere. Carbon-13 to carbon-12 ratio elevated. Argon-38 to argon-36 ratio 1.6 times Earth's value. This fractionation proves preferential loss of light isotopes to space over billions of years. Light atoms escape more easily than heavy atoms. The atmosphere's isotopic signature is forensic evidence of massive historical loss. Paul Mahaffey led the sample analysis at Mars Instrument on Curiosity, measuring atmospheric composition with unprecedented precision. The smoking gun for atmospheric escape is isotope ratios. Light isotopes escape to space more easily than heavy isotopes over billions of years. This fractionation proves Mars lost most of its water and atmosphere to space. The current thin, dry atmosphere is a remnant of a much thicker, wetter past. Mars is like a crime scene. Isotope ratios are the forensic evidence revealing what happened. The victim, a once habitable planet. The cause of death, magnetic field collapse and atmospheric stripping. By approximately 3 billion years ago, Mars had transitioned to the cold, dry climate persists today. Atmospheric pressure dropped below the triple point of water, 610 pascals. Below this pressure, liquid water cannot exist at the surface, regardless of temperature. It either freezes or sublimates directly to vapor. Lakes evaporated or froze solid. Rivers ceased flowing. The carving of valley networks stopped. Mars entered an ice age that has lasted 3 billion years to the present. The habitable window closed. The wet planet became a frozen desert. Bruce Joukowsky serves as principal investigator for the MAVEN mission, Mars Atmosphere and Volatile Evolution, which began orbiting Mars in 2014. MAVEN measures how Mars is losing atmosphere to space right now. About 100 grams per second during quiet solar conditions, increasing to several kilograms per second during solar storms. We can extrapolate backward. If this loss rate continued for billions of years, Mars would lose atmosphere equivalent to several Earth atmospheres. That matches isotope evidence of massive atmospheric loss. Ancient Mars was warm and wet, not because it was closer to the Sun or had a different orbit. It had thick atmosphere, creating greenhouse effect. Lost that atmosphere, lost habitability. Yet even as Mars lost its atmosphere and surface water, volcanism continued. The Tharsis volcanic plateau began forming approximately 4 billion years ago. A massive upwelling of mantle material created a bulge elevated 10 kilometers above surrounding plains. Olympus Mons, the largest volcano in the solar system, grew through repeated lava flows over billions of years. 21.9 kilometers tall, with a base diameter of 600 kilometers. Some surfaces possibly as young as 100 million years old. Eruptions on a timescale incomprehensible to human civilizations. Mars's low gravity and lack of plate tectonics allowed these enormous shield volcanoes to build. On Earth, tectonic plates move, carrying volcanoes away from their magma sources. But Mars has no plate tectonics. A single hotspot could erupt in the same location for billions of years. Lava flows accumulated vertically rather than spreading horizontally, creating volcanic mountains 3 times taller than Everest. Olympus Mons's volume reaches approximately 30 million cubic kilometers, 100 times greater than Mauna Loa, Earth's largest volcano. Volcanic outgassing continued to release gases from Mars's interior throughout its history. Carbon dioxide, water vapor, sulfur dioxide added to the atmosphere, partially replenishing what solar wind stripped away. But the replenishment rate never exceeded the escape rate after the magnetic field collapsed. Mars remained cold and dry despite ongoing volcanic activity. The planet could not restore what it had lost. Volcanism fought a losing battle against atmospheric escape. The frozen present was inevitable once magnetic protection vanished. Valles Marineris, the Great Canyon system stretching 4,000 kilometers along Mars's equator, formed primarily through crustal rifting. Approximately 3.5 billion years ago, tectonic stresses associated with the Tharsis uplift cracked the crust. The canyon reaches up to 7 kilometers deep in places. Later widened by erosion, landslides, and possible water flow during Mars's wetter era. This scar across Mars's face records immense geological forces. A planet's crust stretching, breaking under the weight of the largest volcanic province in the solar system. Visible testament to Mars's dynamic geological past. For the last 3 billion years, Mars has been the frozen desert we observe today. Polar caps accumulated over millions of years, composed primarily of water ice at the North Pole, mixed water and carbon dioxide ice at the south. Layered deposits in these caps record climate variations similar to Earth's ice age cycles, preserving a record of orbital changes affecting how solar heating distributes across the planet. Mars's axial tilt varies from 15 to 35 degrees over hundreds of thousands of years, currently 25.2 degrees. These orbital variations create climate cycles, even in the frozen present. Ground-penetrating radar from Mars Reconnaissance Orbiter has revealed extensive subsurface ice. Ice-rich layers buried under meters of dust extend to mid-latitudes, as close as 30 degrees from the equator. Deposited during past climate eras when Mars's axial tilt was higher. Water still exists on Mars in vast quantities, but it's locked away as ice, frozen in polar caps, buried beneath the surface. The planet hasn't lost all its water, just the ability to maintain liquid water at the surface. Ancient oceans frozen and hidden beneath red dust. In 2008, NASA's Phoenix lander touched down at 68 degrees north latitude. Its robotic arm dug a shallow trench and exposed bright material just centimeters below the surface. Over several Martian days, this bright material gradually disappeared, subliming directly from ice to water vapor. Direct confirmation of subsurface water ice just beneath the surface at high latitudes. Validating models predicting ice-rich layers across polar regions. Mars preserves its water, locked in eternal ice, waiting. The ancient valley networks carved 3.5 billion years ago remain clearly visible today. Protected by the thin atmosphere from rapid erosion, these channels appear almost as fresh as when water last flowed through them. On Earth, such features would erode away in millions of years. But Mars's dry climate preserves its climate history. Valley networks testify to lost rivers. Lakebed sediments preserve organic molecules. Clay minerals record long-vanished waters. The planet is a time capsule, its ancient habitability frozen in stone. Curiosity rover has climbed the lower slopes of Mount Sharp in Gale Crater since 2012. Ashwin Vasavada, the mission's project scientist, describes this as driving through time. Mount Sharp is a 5-kilometer tall pile of sedimentary layers, each recording a different climate era. Lower layers show lakebeds from the wet era 3.5 billion years ago. Higher layers show wind-blown dust from dry eras. As Curiosity climbs, we're literally driving through Mars's climate history, reading geological chapters written in stone, traveling forward in time from warm, wet Mars to cold, dry Mars. Kenneth Farley, a Caltech geochemist and expert in crater chronology, explains how scientists date Martian surfaces. We date surfaces by counting craters. More craters means older surface. Heavy Bombardment Era ended approximately 3.8 billion years ago. Valley networks formed 3.8 to 3.5 billion years ago. Clay minerals date to the same era. Sulfates are younger, 3.0 to 2.5 billion years ago. The chronology tells a story: bombardment, then wet era, then drying transition, then frozen desert. Mars's habitable window was brief in geological terms, a few 100 million years, then climate catastrophe. InSight Lander deployed a seismometer on Mars's surface in 2018, operating until 2022. Detecting hundreds of Marsquakes, analyzing how seismic waves traveled through the planet's interior. These measurements revealed crust thickness of 24 to 72 kilometers, mantle extending to 1,560 kilometers depth, liquid core radius of 1,830 kilometers, confirming that Mars differentiated early in its history. The core remains partially molten even today, but it's too cool, too small to generate the convection needed for a dynamo. The magnetic field will never return. Perseverance rover began exploring Jezero Crater's ancient river delta in 2021. Collecting samples of sedimentary rocks transported by an ancient river 3.8 billion years ago. These samples preserve organic molecules and minerals from Mars's warm, wet era. Sealed in titanium tubes, awaiting a future sample return mission to bring them to Earth, where laboratories can analyze them with instruments too large and complex to send to Mars. Searching for biosignatures, evidence of ancient Martian life. The answer to whether we are alone, potentially locked in rocks collected by a robot on another world. David Brain, a Maven team scientist at the University of Colorado, reflects on Mars as a cautionary tale. Mars is an Earth-sized planet in the habitable zone that lost its habitability. It had water, atmosphere, magnetic field, maybe even life. Then lost everything when the magnetic field collapsed and atmosphere escaped to space. This is a cautionary tale. Planetary climates aren't stable over billions of years. Small planet, weak gravity, magnetic field failure. Mars became uninhabitable. Earth is larger, has stronger gravity, maintains its magnetic field. But even Earth isn't guaranteed eternal habitability. Mars reminds us planetary environments are fragile, contingent on factors beyond just distance from a star. Habitability is precious and can be lost. Carl Sagan reflected on the Viking landers' ambiguous life detection results in 1976. The Viking experiments taught us Mars is more chemically complex than we imagined. Did we find life? Probably not. Did we prove life doesn't exist? Definitely not. We tested 2 sites on a planet with surface area equal to Earth's land. Imagine aliens landing in Antarctica and Death Valley, concluding Earth is sterile. Mars deserves more thorough examination than 2 sampling sites. The question remains open, waiting for future missions, future discoveries. Percival Lowell built an observatory in Arizona in 1894, specifically to study Mars. He mapped intricate canal networks he believed were artificial. The canals are too geometrically perfect to be natural, he declared. A dying civilization desperately brings water from polar caps to equatorial cities. He was completely wrong about canals. They were optical illusions, the brain connecting random dark patches into lines. Yet Lowell's passionate conviction inspired generations of planetary scientists. Sometimes being wrong in interesting ways advances science more than being boringly correct. His error motivated the search for truth. Mars's history spans 4.6 billion years, from molten newborn to frozen present. Formation, and differentiation. Magnetic field generation. Heavy bombardment. Warm, wet, habitable era. Magnetic collapse. Atmospheric stripping. Climate catastrophe. Frozen desert persisting to today. All of this deep time compressed into your awareness as you rest here. Billions of years flowing past your consciousness. Planetary evolution as meditation. Deep time as pathway to peace. Tonight you have witnessed the complete biography of another world. Watched a planet form from dust. Observed magnetic field generation and collapse. Seen rivers carve valleys that remain visible billions of years later. Mars teaches us that planetary environments evolve. What was can become what is not. Warm becomes cold. Wet becomes dry. Habitable becomes hostile. All over timescales measured in hundreds of millions of years. As you rest now, Mars continues its orbit. 1.88 Earth years per Martian year. 687 days each orbit around the Sun. Rovers continue exploring ancient lake beds. Orbiters continue mapping crustal magnetism. Scientists continue piecing together climate history from rocks billions of years old. The planet persists, frozen monument to lost habitability. And you rest, understanding deep time, at peace with planetary evolution. Sleep well. Olympus Mons grew through billions of years of repeated lava flows. The youngest surfaces may be only 100 million years old. Some flows date to 2.4 billion years ago. Total volume exceeds 30 million cubic kilometers, 100 times larger than Mauna Loa. Mars's low gravity and stationary crust allowed single hotspot to build enormous shield volcanoes. Lava flows accumulated vertically rather than spreading horizontally. No plate tectonics moved the crust. This created the largest volcanoes in the solar system. Valles Marineris stretches 4,000 kilometers long and reaches 7 kilometers deep. The canyon formed primarily through crustal rifting. Tectonic stresses from Tharsis uplift cracked the crust approximately 3.5 billion years ago. Later widened by erosion and landslides. Billions of years of volcanism released gases from Mars's interior, carbon dioxide, water vapor, and sulfur dioxide added to the atmosphere. This partially replenished what solar wind stripped away, but insufficient to maintain thick atmosphere. The loss rate exceeded outgassing rate after magnetic field collapsed. Mars could not retain what volcanism provided. The atmosphere continued thinning despite volcanic contributions. The planet dried, cooled, transformed. Kenneth Farley explains how scientists date Martian surfaces by counting craters. More craters means older surface. Heavy bombardment ended approximately 3.8 billion years ago. Surfaces with few craters are younger. Some on Olympus Mons, possibly 100 million years old. Valley networks formed between 3.8 and 3.5 billion years ago. Clay minerals date to the same era. Sulfates are younger. The chronology tells a story. Bombardment, wet era, drying transition, then frozen desert. Mars's habitable window was brief in geological terms. A few 100 million years of suitable conditions. Then, climate catastrophe. The transformation took longer than habitability lasted. Brief window, long decline. Around 4 billion years ago, Mars's small core cooled below the threshold for dynamo. The magnetic field shut down. The protective magnetosphere vanished. Solar wind began directly impacting upper atmosphere. Jack Canerney describes the consequences. When core cooled and dynamo died, protection vanished. Solar wind began directly stripping atmosphere. Over hundreds of millions of years, Mars lost 99% of its air to space. The timing matches exactly. Magnetic field died 4 billion years ago. Atmospheric loss accelerated immediately after. Warm, wet climate ended. Magnetic death sentence for habitability. Without magnetic protection, solar wind particles collided with atmospheric molecules, ionizing them, accelerating them to escape velocity. Light isotopes preferentially escaped. Over hundreds of millions of years, atmosphere thinned dramatically. Greenhouse effect weakened. surface temperatures dropped. The air became thinner with each passing million years. What remained could no longer hold warmth. Mars entered permanent cooling. The dying had begun. Bruce Joukowsky leads the MAVEN mission, measuring how Mars loses atmosphere today. About 100 grams per second normally, several kilograms per second during solar storms. Extrapolating backward reveals massive historical loss. MAVEN's measurements confirm ancient Mars was warm and wet. Not because it was closer to the Sun or different orbit. It had thick atmosphere, creating greenhouse effect. Lost that atmosphere, lost habitability. Modern Martian atmosphere shows extreme heavy isotope enrichment. Deuterium to hydrogen ratio, 5 times Earth's value. Carbon-13 to carbon-12, elevated. Argon-38 to argon-36 ratio, 1.6 times Earth's. This fractionation proves massive atmospheric escape. Paul Mahaffey calls isotope ratios the smoking gun. Light isotopes escape to space more easily than heavy isotopes. This happens over billions of years. The fractionation proves Mars lost most of its water and atmosphere. Current thin atmosphere is remnant of much thicker past. Mars is like crime scene. Isotope ratios are forensic evidence, revealing what happened across deep time. By approximately 3 billion years ago, atmospheric pressure dropped below the triple point of water, 610 pascals. Liquid water became thermodynamically unstable at surface. Lakes evaporated or froze. Rivers ceased flowing. Valley carving stopped. The wet era ended. Mars entered Ice Age, lasting 3 billion years to present. Tharsis volcanism continued for billions of years, partially replenishing atmosphere through outgassing. But outgassing rate never exceeded escape rate. Mars remained cold, dry, hostile. David Brain reflects on Mars as a cautionary tale. Earth-sized planet that lost its habitability. Had water, atmosphere, magnetic field, maybe even life. Then lost everything. Small planet, weak gravity, magnetic field failure. Mars became uninhabitable. This is cautionary tale. Planetary climates aren't stable over billions of years. Planetary environments are fragile, contingent on factors beyond just distance from star. Habitability is precious and can be lost. For the last 3 billion years, Mars has been frozen desert. Polar caps accumulated, subsurface ice deposits formed. Surface remained geologically active. Landslides, dust storms, seasonal carbon dioxide cycles, but no liquid water, no habitability. Frozen monument to lost climate. Polar caps are primarily water ice at North Pole, mixed water and CO2 ice at South Pole, accumulated over millions of years. Layered deposits record climate variations. similar to Earth's ice age cycles. Preserve record of orbital changes affecting solar heating distribution. Frozen history in ice. Ground-penetrating radar reveals extensive subsurface ice across mid-latitudes extending to 30 degrees from equator. Ice-rich layers buried under meters of dust. Hidden water. Deposited during past climate eras, when Mars's axial tilt was higher. Obliquity varies 15 to 35 degrees over hundreds of thousands of years. Currently 25.2 degrees. Ashwin Vasavada describes Mount Sharp in center of Gale crater. 5-kilometer tall pile of sedimentary layers, each layer recording different climate era. History written in stone. Lower layers show lake beds from wet era, 3.5 billion years ago. Higher layers show wind-blown dust from dry eras. As curiosity climbs, we drive through time. Climbing higher is traveling forward in time, from warm, wet Mars to cold, dry Mars. Reading climate history vertically. Geological book. Valley networks carved 3.5 billion years ago remain visible, protected by thin atmosphere from rapid erosion. Clay minerals formed in ancient lakes, detectable from orbit. Gale craters' lakebed sediments preserve organic molecules. Jezero's river delta awaits detailed sampling. Mars's dry climate preserved climate history. would erode on wet Earth. Curiosity and perseverance explore ancient terrains, analyzing rocks formed during warm, wet era. Insight measured interior structure, confirming early differentiation. MAVEN quantifies ongoing atmospheric loss. Orbiters map magnetic anomalies, recording dead dynamo. Human technology reads Mars's biography, written in stone. Kenneth Farley explains crater chronology. Valley networks formed 3.8 to 3.5 billion years ago. Clay minerals date to same era. Sulfates younger. The chronology tells story. Bombardment, wet era, drying transition, frozen desert. Mars's habitable window was brief. Few 100 million years, then climate catastrophe. Brief window, long decline. Olympus Mons stands 21.9 kilometers tall. Its youngest lava flows formed 100 million years ago. Volcanism persisted. Mars's low gravity allowed single hotspots to build enormous shields. Lava accumulated vertically over billions of years. Darcy's volcanic plateau began forming 4 billion years ago. It contains 25% of Mars's mass above reference datum. Volcanic outgassing released gases from Mars's interior for billions of years. CO2 and water vapor replenished atmosphere. But outgassing never exceeded atmospheric loss rate. Solar wind stripped faster than volcanoes could replace. By 3 billion years ago, Mars entered Ice Age. An ice age lasting 3 billion years to present. Polar ice caps accumulated over millions of years. Layered deposits record ancient climate variations like tree rings. Subsurface ice exists across mid-latitudes. Ground-penetrating radar reveals ice-rich layers buried under dust meters deep. Mars's axial tilt varies from 15 to 35 degrees. Currently 25.2 degrees, creating seasonal patterns. These orbital variations affect solar heating distribution. Ice deposits formed during past high obliquity eras. Modern Mars is frozen monument to lost habitability. Valley networks carved billions of years ago remain visible. Thin atmosphere preserves ancient features from rapid erosion. Mars's dry climate protects its geological history. Curiosity rover climbs Mount Sharp, reading climate layers. Lower layers show wet era. Higher layers show dry. Perseverance explores Jezero Crater's ancient river delta, sampling sedimentary rocks transported by rivers 3.8 billion years ago. These samples preserve organic molecules and minerals. They await future return to Earth for detailed analysis. InSight measured Mars's interior structure through seismology. Hundreds of Marsquakes revealed crust, mantle, and liquid core. The core radius measures 1,830 kilometers, confirming Mars differentiated early and core remains partially molten. Mars teaches that habitability is fragile. Planetary environments evolve over deep time. Small planet, weak gravity, magnetic field failure. What was warm became cold. What was wet became dry. Habitable became hostile. Over timescales measured in billions. David Brain observes Mars as cautionary tale. Planetary climates aren't stable. Mars lost everything, while Earth thrived nearby. Habitability is precious and can be lost. Tonight, you've compressed 4.6 billion years into peaceful understanding. Deep time flows, patient geological rhythms. Billion-year transformations. Incomprehensible, yet comprehended. Mars continues orbit 687 days each year. Rovers explore ancient lake beds, scientists piece together climate history. Written in stone, billions of years old. Valleys carved when Earth was sterile. Lakes formed when life on Earth was single cells.